First, we'll talk about CoAP, IETF CoAP. CoAP protocol basically is a REST protocol that makes each lightweight device a server. So it's the sensor device itself, the battery-powered sensor or whatever, is the server, and the application software acts as a client. And the CoAP endpoint can be both client and server. So two devices can talk to each other in a peer-to-peer pattern by being clients and servers to each other, in addition to the software application connecting to a single sensor. The use cases for CoAP were determined by wanting to connect constrained devices to the internet at large. So on the right-hand side of the use cases, we have all the constrained networks, caching, resource discovery, providing for sleeping nodes and limited resources, providing low latency and multicast connectivity, all the things that are needed on sensor networks. Then we have a proxy that can convert the CoAP protocol to HTTP, where we provide the access using standard web protocols. But CoAP can also be used directly between the server and the constrained device over the internet as well. CoAP is a full internet protocol and can be carried over the internet and through switches and routers and all of the standard internet infrastructure. So basically, CoAP connects constrained devices to web services. The scope of CoAP is providing a transport protocol, some base messaging, and REST semantics, and an additional feature of asynchronous notification. So the transport layer is based on UDP primarily with DTLS security, but TCP can also be used, and CoAP can also be used over SMS. Then the base messaging layer provides for reliable message exchange between endpoints. And there are confirmable and non-confirmable messages. Confirmable messages provide acknowledgments for reliable transport, and non-confirmable messages provide a fire and forget sort of functionality for high bandwidth data communications. And then on top of the base messaging, CoAP provides REST semantics. So it maps a REST API with get, put, create, and delete verbs on top of the binary protocol, the binary packet protocol. And so there are REST API commands, get, put, create, and delete, as well as responses that are very similar to HTTP. For example, if a request is made to a data item that doesn't exist, CoAP returns 4.04, which is analogous to an HTTP 404 resource not found response type. And then lastly, CoAP provides asynchronous notifications, which is a way for the sensor to send data at its own initiative instead of waiting to be pulled by the application using GET. So there is a separate IETF draft for that, but basically it allows the application software to do a single GET and allows the sensor device to return multiple responses anytime the data changes. So CoAP maps an HTTP protocol to the binary format. And you can see here the request codes, message IDs, and other optional data are binary encoded into the packet. The minimum CoAP packet size is shown in the top row here. It's 4 bytes. You need the version, the header part, the request code, and the message ID, and that is a complete CoAP packet. An example of a CoAP transaction looks very much like HTTP, where you have a client sending a GET request to a server. The client is the application in this case, and the server is the CoAP sensor. The client wants to do a confirmable transaction and wants to get the value of the light resource. So the client sends a GET to the server, and the server responds with an ACK and the data from the light resource. It responds with the content. CoAP allows proxy caching also. So in the case of the GET here, if there was a proxy cache between the client and the server, and here we have the client on the right-hand side of the diagram, just to and the server on the left. So the sensor is on the left, and the application client is on the right, and the proxy is between them. The client does a GET of the light, In this case, the proxy did not find that value in the cache, so the proxy does a get to the sensor. The sensor returns the content, returns the value to the proxy, along with max age, which says that this value is valid for 30 seconds in this case. And then the proxy responds back to the client. In this case, the client doesn't really know whether the data lived in the proxy or in the server. It basically did a get, and it got a response. So now the proxy has the data. If another client or the same client does a get request again, the proxy can respond directly from the fresh cache value with the value. And in each case, the HTTP client had no idea whether it was getting a value from the proxy or from the server itself. The only way it could tell it's getting a value from the server is that it would take a little longer for the value to be returned. It would have to make another CoAP transaction in addition to the HTTP transaction. Asynchronous notification is added to CoAP as a way of providing the CoAP server a way to let the client know when the value of a resource changes. So this shows the transaction flow for asynchronous notification. The application client does a get to the server, to the sensor of the light resource, specifying observe 0 and specifying a token. The CoAP server, which is the sensor, remembers the token and uses it to associate responses with that get. So the first response is an acknowledge, returning the value of the light resource. And then at some time in the future, the light resource might change, and the CoAP server then will be able to send a subsequent response, which just is another confirmable transaction to the client that says this light has changed. It basically says it has the observed value in it and it has the token, so then the client knows which response which request to match with the response. And from then on, anytime the value of the resource changes, the server will be able to send an update back to the client. So it's a continuous stream of updates based on when the value of the resource changes, or any other time really that the CoAP server decides to send an update back to the client. Okay. CoAP and related specifications provide web linking for machines and semantic linking. That's similar to web linking between browsers and web servers, but this is particularly for machine-to-machine communication. The main difference is that the semantic content of these links describes information which is more relevant for machine-to-machine communication. So RFC 6690 is an IETF specification that defines the format of semantic links for machine-to-machine in core, in CoAP. Basically, it defines a well-known resource where the links are stored, and it defines how string parameters are passed in as queries so that resources can be discovered by attribute, by relation, and by their metadata values. And RFC 6690 core links can be used with unicast or multicast transactions. And they use the regular REST API. So the format of an RFC 6690 link contains a pointer to the resource, which in this case is the path 4001/0/9002 in brackets. And then it contains a number of relations that describe that resource. So here it's saying resource type, RT, equals OMA lightweight M2M, saying that this is an OMA lightweight M2M type resource. CT says content type. This is 50s, which is a binary encoding that maps to JSON in this case. And also it says observable equals 1, which says that indicates that the client can do observed transactions and do asynchronous notification to this resource. Local network discovery relies on a well-known location, actually called well-known, which is an HTTP standard as well. And this location is called well-known core, which is where the metadata for a CoAP resource are stored. So to do local network discovery, if the CoAP client knows what the address of the server, it can do a get to well-known core, a resource of the server, and the server will return back the content. It could also use multicast, and if any server has a well-known core, it would return its content. So for example, in a network that supports multicast, the client could use multicast to discover resources from multiple servers. So for example, if a network had one client and 4 CoAP servers, the client could do a multicast get to well-known core, and each server would return its link content from the well-known core resource. For an example of the link content shown below here, so for each resource, a number of relations are returned that describe that resource. Resource discovery can also be done in a centralized way. There's another draft in IETF called Core Resource Directory that provides a centralized place for links to be stored from CoAP servers, from the sensor devices, and discovered by applications. So what happens here is the CoAP servers register their links with the resource directory by doing a post transaction, and then applications can do get transactions to discover those links and retrieve the pointers to those resources. So for example, here's an example of an endpoint registering with the resource directory by posting its links. The resource directory returns a response saying, yes, I created that, and here's a location for you to do management. From then on, then other endpoints can do discovery by doing a lookup, a get of an RD lookup resource, and specify some query parameters about what sorts of resources it wants to discover. The RD service then returns the links that match those resources.